Do that.
Can you hear me?
We can hear you.
Okay.
Have you tested the video?
We are getting started.
Okay.
Okay, so I'm going to play a video for chapter 5, and then we are going to solve some questions, but watch it very carefully, okay?
There's no jokers in it. You could do the same problems with the joker, you'll just get slightly different numbers. So with that out of the way, let's first just think about how many cards we have in a standard playing deck. So you have 4 suits. And the suits are the spades, the diamonds, the clubs, and the hearts. You have 4 suits, and then in each of those suits, you have 13 different types of cards, or sometimes it's called the rank. So each suit has 13 types of cards. You have the ace, then you have the 2, the 3, the 4, the 5, the 6, 7, 8, 9, 10, and then you have the jack, the king, and the queen, and that is 13 cards. So you can have, for each suit, you can have any of these. For any of these, you can have any of the suits. So you can have a jack of diamonds, a jack of clubs, a jack of spades, or a jack of hearts. So if you just multiply these things, you could take a deck out playing cards and actually count them, take out the jokers and count them. But if you just multiply this, you have 4 suits. Each of those suits have 13 types. So you're going to have 4 times 13 cards, or you're going to have 52 cards in a standard playing deck. Another way you could say it, you're like, look, there's 13 of these ranks or types, and each of those come in 4 different suits. 13 times 4, once again, you would have gotten 52 cards. Now, with that out of the way, let's think about the probabilities of different events. So let's say I shuffle that deck. I shuffle it really, really well, and then I randomly pick a card from that deck. And I want to think about what is the probability that I pick. What is the probability that I pick a jack? Well, how many equally likely events are there? Well, I could pick any one of those 52 cards. So there's 52 possibilities when I pick that card. And how many of those 52 possibilities are jacks? Well, you have the jack of spades, the jack of diamonds, the jack of clubs, and the jack of hearts. There's 4 jacks. There's 4 jacks in that deck. So it is 4 over 52. These are both divisible by 4. 4 divided by 4 is 1. 52 divided by 4 is 13. Now let's think about the probability. So we're going to start over. I'm going to put that jack back in. I'm going to reshuffle the deck. So once again, I still have 52 cards. So what's the probability that I get a hearts? What's the probability that I just randomly pick a card from a shuffle deck and it is a heart? The suit is a heart. Well, once again, there's 52 possible cards I could pick from, 52 possible equally likely events that we're dealing with. And how many of those are hearts? Well, essentially 13 of them are hearts. For each of those suits, you have 13 types. So there are 13 hearts in that deck. There are 13 diamonds in that deck. There are 13 spades in that deck. There are 13 clubs in that deck. So the 13 of the 52 would result in hearts. And both of these are divisible by 13. This is the same thing as 1/4. 1 in 4 times, I will pick it out, or I have a 1 in 4 probability of getting a hearts when I go to that, when I randomly pick a card from that shuffle deck. Now let's do something that's a little bit more interesting, or maybe it's a little obvious. What's the probability that I pick something that is a jack? I'll just write J. It's a jack and it is a hearts. It is a jack and it is a hearts. Well, if you're reasonably familiar with cards, you'll know that there's actually only one card that is both a jack and a heart. It is literally the jack of hearts. So we're saying, what is the probability that we pick the exact card, the jack of hearts? Well, there's only one event, one card that meets this criteria right over here, and there's 52 possible cards. So there's a 1 in 52 chance that I pick the jack of hearts, something that is both a jack and it's a heart. Now let's do something a little bit more interesting. What is the probability? You might want to pause this and think about this a little bit before I give you the answer. What is the probability of, so once again, I have a deck of 52 cards. I shuffle it, randomly pick a card from that deck. What is the probability that that card that I pick from that deck is a jack or a heart? So it could be the jack of hearts, Or it could be the jack of diamonds, or it could be the jack of spades, or it could be the queen of hearts, or it could be the two of hearts. So what is the probability of this? This is a little bit more of an interesting thing because we know first of all that there are 52 possibilities. There are 52 possibilities, but how many of those possibilities meet the criteria, meet these conditions that it is a jack or a heart? And to understand that, I'll draw a Venn diagram. Sounds kind of fancy, but nothing fancy here. So imagine that this rectangle I'm drawing here represents all of the outcomes. So if you want, you can imagine it has an area of 52. So this is 52 possible outcomes. Now, how many of those outcomes result in a jack? So we already learned 1 out of 13 of those outcomes result in a jack. So I could draw a little circle here where that area, and I'm approximating, that represents the probability of a jack. So it should be roughly 1/13 or 4/52 of this area right over here. So I'll just draw it like this. So this right over here is the probability of a jack. The probability of the jack. It is 4. There's 4 possible cards out of the 52. So that is 4/52 or 1 out of 13. 1/13. Now, what's the probability of getting a hearts? I'll draw another little circle here that represents that. 13 out of 52. 13 out of these 52 cards represent a heart. And actually, one of those represents both a heart and a jack. So I'm actually going to overlap. Hopefully, this will make sense in a second. So there's actually 13 cards that are a heart. So this is the number of hearts. Number of hearts. And actually, let me write this top thing that way as well. It makes it a little bit clearer that we're actually looking at. Clear that. So the number of jacks. Number of jacks. And of course, this overlap right here is the number of jacks and hearts, the number of items out of this 52 that are both a jack and a heart. It is in both sets here. It is in this green circle and it is in this orange circle. So this right over here, I'll do that in yellow since I did that problem in yellow. This right over here is the number of jacks and hearts. So let me draw a little arrow there. Getting a little cluttered. I should draw a little bit bigger. Number of jacks and hearts. Number of jacks and hearts. And that's an overlap. So what is the probability of getting a jack or a heart? So if you think about it, the probability is going to be the number of events that meet these conditions over the total number of events. We already know the total number of events, 52, but how many meet these conditions? So it's going to be the number, it's going to be, you could say, well, look, the green circle right there says the number that gives us the jack, and the orange circle tells us that the number that gives us a heart. So you might want to say, well, why don't we add up the green and the orange? But if you did that, you would be double counting. Because if you added up, if you just did 4, if you did 4 plus 13, what are we saying? We're saying that there are 4 jacks, and we are saying that there are 13 hearts. But in both of these, when we do it this way, in both cases, we are counting the jack of hearts. We're putting the jack of hearts here, and we're putting the jack of hearts here. So we're counting the jack of hearts twice, even though there's only 1 card there. So you would have to subtract out where they're common. You would have to subtract out the item that is both a jack and a heart. So you would subtract out the 1. Another way to think about it is you really want to figure out the total area here. You want to figure out the total area here. You want to figure out this total area. Let me zoom in and I'll generalize. So if you have one circle like that, and then you have another overlapping circle like that, and you wanted to figure out the total area of both of the circles combined, you would look at the area of this circle, you would look at the area of this circle, and then you could add it to the area of this circle. Well, when you do that, you'll see that when you add the 2 areas, you're counting this area twice. So in order to only count that area once, you have to subtract that area from the sum. So if this area has A, this area is B, and the intersection where they overlap is C, the combined area is going to be A plus B minus where they overlap, minus C. So that's the same thing over here. We're counting all the jacks, and that includes the jack of hearts. We're counting all the hearts, and that includes the jack of hearts. So we counted the jack of hearts twice, but we have to subtract 1 out of that. So it's going to be 4 plus 13 minus 1, or this is going to be 1650 seconds. And both of these things are divisible. Both of these things are divisible by 4. So this is going to be the same thing as divide 16 by 4, you get 4. 52 divided by 4 is 13. So there's a 4/13th chance that you get a jack or a hearts. Strange games. And you walk up to a table, and on that table there is an empty bag. And the guy who runs the table says, look, I've got some marbles here, 3 green marbles, 2 orange marbles, and I'm going to stick them in the bag. And he literally sticks them into the empty bag to show you there's truly 3 green marbles, and 2 orange marbles. 2 orange marbles. And he says the game that I want you to play, or that you choose to play, is you're going to look away, stick your hand in this bag. The bag is not transparent. Feel around the marbles. All the marbles feel exactly the same. And if you're able to pick 2 green marbles, if you're able to take 1 marble out of the bag, it's green, you put it down on the table, then put your hand back in the bag and take another marble, and if that one is also green, then you're going to win the prize. You're going to win the prize of, you're going to win $1 if you get 2 greens. If you get 2 greens, you're going to win $1. We said, well, this sounds like an interesting game. How much does it cost to play? And the guy tells you it is 35 cents. 35 cents to play. So obviously, fairly low stakes casino. So my question to you is, would you want to play this game? And don't put the fun factor into it. Just economically, does it make sense for you to actually play this game? Let's think through the probabilities of it. So first of all, what's the probability that the first marble you pick is green? What's the probability that first marble is green? Actually, let me just write first green. Probability first green. First green. Well, the total possible outcomes, there's 5 marbles here, all equally likely. So there's 5 possible outcomes. 3 of them satisfy your event that the first is green. So there's 3/5 probability that the first is green. So you have a 35th chance, 35th probability, I should say, that after that first pick, you're kind of still in the game. Now, what's the probability? What we really care about is your probability of winning the game. You want the first to be green and the second green. Well, let's think about this a little bit. What is the probability that the first is green? First, I'll just write G for green, and the second is green. Now, you might be tempted to say, oh, well, maybe the second being green is the same probability. It's 3/5. I can just multiply 3/5 times 3/5, and I'll get 9/25. Seems like a pretty straightforward thing. But the realization here is what you do with that first green marble. You don't take that first green marble out, look at it, and put it back in the bag. So when you take that second pick, the number of green marbles that are in the bag depends on what you got in the first pick. Remember, we take the marble out. If it's a green marble, whatever marble it is, whatever after the first pick, we leave it on the table. We are not replacing it. So there's not any replacement here. So these are not independent events. Let me make this clear. Not independent, not in particular. The second pick is dependent on the first. Dependent on the first pick. If the first pick is green, then you don't have 3 green marbles in a bag of 5. If the first pick is green, you now have 2 green marbles in a bag of 4. So the way that we would refer to this, the probability of both of these happening, yes, it's definitely equal to the probability of the first green, the probability of the first green, times, now this is kind of the new idea, the probability of the second green, given this little line right over here, just this straight up vertical line, just means given. This means given that the first was green. Now, what is the probability that the second marble is green, given that the first marble was green? Well, we draw through the scenario right over here. If the first marble is green, there are 4 possible outcomes, not 5 anymore, and 2 of them satisfy your criteria. 2 of them satisfy your criteria. So the probability of the first marble being green and the second marble being green is going to be the probability that your first is green, so it's going to be 3/5, times the probability that the second is green, given that the first was green. Now you have 1 less marble in the bag, and we're assuming that the first pick was green, so you only have 2 green marbles left. And so what does this give us for our total probability? Let's see, 3/5 times 2/4. Well, 2/4 is the same thing as 1/2. This is going to be equal to 3/5 times 1/2, which is equal to 3/10, or we could write that as 0.30, or we could say there's a 30% chance of picking 2 green marbles when we are not replacing. So given that, let me ask you the question again. Would you want to play this game? Well, if you played this game many times, on average, you have a 30% chance of winning $1. And we haven't covered this yet, but so your expected value is really going to be 30% times $1. This gives you a little bit of a preview, which is going to be 30 cents. 30 cents, 30% chance of winning $1. You would expect, on average, if you play this many times, that playing the game is going to give you 30 cents. Now, would you want to give someone 35 cents to get on average 30 cents? No, you would not want to play this game. Now, one thing I will let you think about is, would you want to play this game if you could replace the green marble, the first pick, after the first pick? If you could replace the green marble, would you want to play the game in that scenario? Let's do another one of these dependent probability problems. You have 4 coins in a bag. 3 of them are unfair in that they have a 45% chance of coming up tails when flipped. The rest are fair. So for the rest of them, you have a 50% chance of tails or a 50% chance of heads. You randomly choose 1 coin from the bag and flip it 4 times. What is the percent probability of getting 4 heads? So let's think about it. When we put our hand in the bag, we take one of the coins out. There's some probability that we get an unfair coin, and 3 of the 4 coins are unfair. So there's 3/4 probability that we get an unfair coin, and then there's only 1 out of the 4 coins that's fair. So there was a 1/4 probability that I get a fair coin. Now, given that I have, so unfair, let's remind ourselves, unfair coin has a 45% chance of coming up tails. So this means that I have a 45% chance of tails, which also means we have to be careful here because they're asking us about heads. If I have a 45% chance of getting tails, that means I have a 55% chance of getting heads, right? Whatever, I have a 100% chance of getting one of these two. If it's 45% for tails, 100 minus 45 is 55 for heads. For the fair coin, I have a 50% chance of tails and a 50% chance of heads. 50% heads. Fair enough. Now, I want to know in either of these scenarios, what is the percent probability of getting 4 heads? So if given I've got the unfair coin, the probability of getting 4 heads is going to be 55% for each of those flips. So the probability of getting exactly 4 heads is going to be, it's actually going to be 0.55 times 0.55 times 0.55 times 0.55. And so the probability of picking an unfair coin and getting 4 heads in a row is going to be equal to 3/4 times all of this business over here. So that's 3/4 times, and this is 0.55 times itself 4 times. So I could write it as 0.55 to the 4th power. And we'll get the calculator out in a second to actually calculate what this is. Now let's do the same thing for the fair coin. If I did pick a fair coin, the probability of getting heads 4 times in a row is going to be 0.5 times 0.5 times 0.5 times 0.5, or the probability of getting the fair coin, which is 1/4 probability, 1/4 chance, times the probability, and getting 4 heads in a row is going to be 1/4 times all of this. So it's going to be 1/4 times, this is just 0.5 times itself 4 times, so that's 0.5 to the 4th power. So let's get the calculator out to calculate either one of these. So we get 3 divided by 4, 3 divided by 4 times, and it knows that when I do the multiplication, it's not in the denominator here. So 3/4 times, I'll just do it in parentheses, which I don't have to do it in parentheses because it knows order of operations. So 0.55 to the 4th power is equal to 0. Let me write it down. Let me take it off the screen so I can write it down properly. Actually, let me just do both of these calculations. So this probability is that one right over there. And then this one down here is 1 divided by 4 times 0.5 to the 4th power. So it's equal to that right over there. And so let's just be clear. The probability of picking the unfair coin and then getting 4 heads in a row is this top number. It's like roughly 6.9% chance that you get the unfair coin and then get 4 heads in a row. The probability that you get the fair coin and then get 4 heads in a row is even lower. It's only a 1.6% chance. Now, the probability of getting 4 heads in a row either way is going to be the sum of this and this, or the sum of that and that, which is going to be, keep my calculator out, so it's going to be equal to, I can just take the previous answer, let me just retype it so I don't confuse you. So 0.015625 plus 0.068629, what is it, 296875. I'm going to round it anyway, so it doesn't matter too much. So if I take the sum, let me take this off screen, and then I can still see it, and then we write it. So what I got here, this one is 0.068629, and I'll round it 7. And this down here was 0.015625. When you add these two up, because we just care about getting 4 heads, either way, this is the probability of getting it this way with the unfair coin. This is the probability of getting it with the fair coin. We want it either way, so let's add the 2, which we already done our calculator. So if you add that number to that number, you get 0.08425, and it keeps going. But I'm just going to round it. So this is the same thing as, this is equal to 8.425%, if I want to round it a little bit more, 8.43% chance of getting 4 heads in a row. And once again, that's a slightly higher number than if all of the coins were fair, because there's a 3/4 chance that I get a coin that has a better than even chance of getting heads. So that's why this number is going to be a little bit higher than the probability of a fair coin of just getting 4 heads in a row. A marching band is holding a raffle at a football game with 2 prizes. After the first ticket is pulled out and the winner determined, the ticket is taped to the prize. The next ticket is pulled out to determine the winner of the second prize. Are the 2 events independent? Explain. Now, before we even think about this exact case, let's think about what it means for events to be independent. It means that the outcome of one event doesn't affect the outcome of the other event. Now, in this situation, the first event, after the first ticket is pulled out and the winner determined, the ticket is taped to the prize. Then the next ticket is pulled out to determine the winner of the second prize. Now, the winner of the second prize, the possible winners, the possible outcomes for the second prize is dependent on who is filled out for the first prize. You can imagine if there's 3 tickets, let's say there's tickets A, B, and C in the bag, and for the first prize, they pull out ticket A. they pull out ticket A. That's for the first prize. For the first prize. Now, when we think about who could be pulled out for the second prize, it's only going to be tickets B or C. It'll only be tickets B or C. Now, the first prize could have gone the other way. It could have been A, B, and C. The first prize could have gone to ticket B. And then the possible outcomes for the second prize would be A or C. So the possible outcomes for the second event, for the second prize, are completely dependent on what happened or what ticket was pulled out from for the first prize. So these are not independent events. The second event, the outcomes for it are dependent on what happened in the first event. So they are not independent. The way that we could have made them independent is after the first ticket was pulled out, if they just wrote down the name or something, and then put that ticket back in. Instead, they taped to the prize. But if they put that ticket back in, then the second prize, it would have still had all the tickets there. It wouldn't have mattered who was picked out in the first time because their name was just written down, but their ticket was put back in, and then you would have been independent. So if you would replace the ticket, you would have been independent. But since they didn't replace the ticket, they taped to the prize. These are not independent events.
Jefferson, here's a similar problem. Let's see if you can get it right. Can you hear me, Jefferson?
Yeah.
How will you approach this problem? I'll give 5% credit to the person who answers this correctly. But by 5% credit, I mean like it's the same as if you got 5% for your homework. So like if you answered 20 of these correctly, it's like you got a homework for free.
I got it.
Yes. How will you approach it? I'm not asking the correct answer. I want you to know if you demonstrate, if you understand the concepts.
Yeah, so
I don't even care about the numeric answer.
Yeah, so you have 9 marbles in total, and you will pick a marble twice. So the first one is I'll just explain the whole problem and how I approached it. So the first one is that you pick a green one, which is 3/9, and then you don't put the marble back, which means there are 8 marbles remaining. If you then consider taking a red marble, the probability is 2/8, and then you multiply 3/9 and 2/8, and you get 1/12. That's the probability.
But that's like an ad hoc answer. Like I want you to answer this theoretically. Like what concepts did we use?
So it's dependent because the second event is dependent on the first.
Dependence or independence?
Dependent.
Dependence, right?
Yeah.
Yes. And dependence in what sense? Like how would you like illustrate dependence?
So like in this case, the outcome of picking the second marble is dependent on the first event because you take a marble out. So it means that it has an influence on the second event.
How do you define dependence? Like that's again ad hoc. Like I want you to define dependence theoretically. Like here's my question. Can you write down a formula that actually demonstrates you understand the concept of dependence? How would you check for dependence? What are the mathematical conditions for checking for dependence? That's my question. Because in those videos, it was missing, kind of. It was more ad hoc. How many of you read chapter 5? Raise your hand. You know, from now on, you should come to class prepared. How many of you knew we were going to cover chapter 5 tonight? Raise your hand, please. So none of you knew we were going to cover chapter 5 tonight?
I thought you said that we had to read it, but we knew we were covering it, but not that we had to read it.
It's on the syllabus, right? You know, right now I could just see, I looked at the grades for chapter 4 and just about everybody got 100, right? You know, what if I gave you the exact same quiz, right? After you learn all these concepts in theory, would you demonstrate in front of me that you could get 100? How many of you feel that comfortable? I can do it right now. That's not good. That's not good. So, those of you who got 100, right? If I open the quiz for chapter 4, how many of you can demonstrate that they can get 100? Raise your hand.
Well, with the homeworks, you don't need to.
No, right here. I can pull up macro and connect. Can you demonstrate that you actually can earn 100 right now?
We can calculate this.
Just a second. You know, raise your hand before you speak. I want one person speaking at a time. And introduce yourself. Tell me who you are. Yes, who is this?
Pim.
I can't hear you.
Pim.
Who? Okay.
Pim.
Okay, so go ahead.
Yeah, but for the home, like this question, I think everyone here can calculate it, but maybe not explain it as specifically as you want us. But at the homeworks, we also just use the calculator and stuff to, like we did it now, we calculated and we have the good answer. But we just don't know how to explain it as specifically as you want us to explain it. So we think we explain it like that, like how it's supposed to be, but apparently it's not.
No. Those are two separate levels of learning. You know, I'm not asking you demonstrate to me that you understand the concept. I'm asking you to demonstrate that you could get 100 on the homework any way you want right now. How many of you can?
I mean, I didn't make chapter 5 yet, so I don't know.
Not chapter 5, chapter 4. That was my question.
I mean, I hope so. I mean, chapter 4 it worked out, so I hope I will get it again, yeah. But you never know, it's different questions. Maybe you don't get a 100. Yeah, no, I mean,
I have my doubts. You know, when I look at these homeworks, there is a lot of material online. Okay. Who's speaking? Hi, Sarah.
But the thing is that in the homework you can have many attempts, so you can get incorrect and try again. So the fact that we have 100 doesn't mean, you know, like.
There were infinite trials. Okay, that's my bad. In the future, I'm going to remove that. For chapter 5, I removed that. You have only one try.
That doesn't mean we're not going to learn. That means we're going to try again.
No, because I don't want this to be a guessing game. Like, you know, I mean, if you try again and again, there are finite number of possibilities, right? You're not really necessarily learning.
Yeah, but it's not guessing. It means we're trying.
Trying is not good enough. You have to learn. You have to demonstrate that you can learn. We don't give grades for trial. So moving forward, your homeworks will have only one trial. Okay, so anybody else who wants to talk about this question, like we can demonstrate? I'm going to increase the extra credit to 10%. What is the concept?
I haven't read chapter 5.
No, it's okay. You know, so you know why I ask you this question?
I think I
Yes.
can.
Go ahead.
Is it not just P and then between brackets A times B after A? If that's what you wanted in a formula.
Hold on. Say that slowly.
Like the probability of A plus the probability of B after A.
Okay, you mean given,
Okay.
right? Like that.
Multiplied by each other.
But what is the second one?
The probability of B after you picked A.
Okay, that's called conditional probability. You have 10 points.
Okay, thank you.
That
The name is Pim.
Yes. For that 10 points. So, there is no substitute for theoretical knowledge, okay? Sadly, when you watch the video, like these concepts are taught in an ad hoc fashion, okay? So here's my second question. How do you check if events are independent?
Again?
Okay.
Then it's a dependent variable.
Okay, but how would you write that like mathematically? What's the algebra?
Function one inside of two.
But here, what is the function we are talking about? Mathematically, it's the probability function, right? So what needs to be true about probability functions for us to say these two events are independent? Yeah. Well, the probability is very complicated. Looks simple, but it's complicated. Jefferson, did you hear the question?
No, please repeat it.
Here's the question. How do we check if two events are independent? We start with 5 points. If you can answer it correctly, you get 10 points.
Do you want to vote again or not?
JC, right? Who's speaking?
I was asking if you want us to give a formula or just explain the concept.
I couldn't understand you.
I was wondering if you want us to explain the concept or just give a formula.
You have to provide the formula. Let me give you a hint. There are 3 ways of checking for independence. Or you could break it down and say there are 2 ways because one is like the inverse of the other. How do you check for independence? How do you check if 2 events are independent?
Just multiply A and B.
Say it again.
Just multiply A and B instead of.
Okay, so you multiply A and B.
Like
Okay.
expecting
Let's talk about that. I'm so glad I like the way you said it. What are A and B?
the probability of event A and the probability of event B.
No. Like, what is A? What are they? What is A? What is A, for example? Like, what kind of object is it? Like, like, what is it like? What kind of mathematical object is A?
Just depends on the question, like what event A is. For example, here A would be the first probability that the first marble will be green's probability of A.
Okay, so let me help you a little bit. What do we compute probabilities for?
Sorry?
What do we compute probabilities for?
So I really didn't understand.
Okay, what do we compute probabilities for?
Use conditions for A.
In order to know which one is going to be the result,
I couldn't hear you. Can you say that again?
in order to know what is going to be the result, like you compute it in order to know the result.
We need subtitles.
I just said another probability of the result.
No. So, okay. So let's go back, like, let's walk in baby steps, right? So all this probability talk, right? Where does it start? How many of you have read the chapter? Nobody?
We have it open.
A little bit?
Yeah.
Okay. A little bit is not good enough. A lot is not good enough. Like, this is a complicated topic. So, okay. So sleep over those questions. like think about them. You can just email me if you have an answer, and I'll still give you your temper. We started with 5%, but since nobody is able to answer it, we'll go to 10%, okay?
So you wanted that there speaking.
Yes.
I wanted that formula for this independence.
No, because nobody could answer that one, right?
I answered it.
Okay. No, you already got the points for the previous question, okay? You got the points for conditional probability. But what is A, what is B? That was the question. Second question.
The event.
Who said that?
Sarah.
Sarah?
Yes, Sarah. Sarah.
Give Sarah 10 points. Sarah, you got 10 points.
Thank you.
A and B are events. So what do we compute probability for? We compute probability for? Events. Mathematically, how do you represent events?
What is the question?
This is the third question. Mathematically, how do you represent events?
Probabilities.
No. Mathematically, how many of you have learned the concept of variable? Raise your hand. How many of you know the concept of a variable?
Variable has several meanings, so in a certain way, yes.
Okay. So, how many of you have heard the concept of an event? Has anybody taken any probability courses or statistics? Okay. So, how do you represent events mathematically? Okay. Do you remember he drew Venn diagrams, right? Right?
Yeah.
So, in Venn diagrams, you draw events actually. Okay? So the rectangle is called the sample space. It's the set of all outcomes of the experiment. For example, for a coin flip, it'll be a head and a tail. For a die roll, it'll be 1, 2, 3, 4, 5, 6. For two die rolls, it'll be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then it will go all the way down to 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. That's the sample space. If you take combinations of those elements, you call them events. Okay? So mathematically, how do you represent events? What is the mathematical object that you use that takes combinations of elements? What do you call it?
Fractions.
No. Like, what is the mathematical object that takes combinations of elements? Different world actually than the one you're used to. It's called a set. It's called a set. It's a set. Events are sets mathematically. Okay? So you compute probabilities for events. And events are sets. So you compute probabilities for sets. Okay? For example, remember he talked about a card, right? Deck of cards. Right? There are 4 suits, right? Each suit in itself is an event. Okay? And then in each suit you have what? Like basically 1 to 13 cards, right? For each suit. So you could talk of those each 13 as a separate set. And then, of course, he skipped it. When you deal with sets, you cannot do addition. You cannot do multiplication. You cannot do division. You cannot do subtraction. What do you do instead? You do something completely different, right? You define new operations. For sets, you have 3 sets of operations. For arithmetic, you have 4 operations. For algebra, you are used to 4 operations. But the world of mathematics is much larger. So what do? You have 3 operations. The first operation is intersection. Remember, he drew the Venn diagram? And one set had 4 elements. The second set had 13 elements, right? and one of them was common. And he used the word and. Everybody remember? The word and, A and B, right? Joker and hearts. That word and is the operation of intersection, elements that belong to A and B. Okay? The second operation is complementation. If an element belongs to a set, does not belong to rather a set, all the elements that don't belong to a set, we call that operation complementation. Let me ask you, okay, so what is the complement of the set of parts or the suite of parts? It's the other three suites, right? It's the other three suites. So that is complementation. That's the second operation. What was the third operation he talked about? It was union. But he didn't talk about it explicitly. He was just introducing you to probability in an ad hoc manner, right? What is the danger learning probability in an ad hoc manner?
Small change, you don't know how to deal with it.
Exactly. Say that again. That's the words of a wise man.
Any small change, you don't know how to deal with it.
There's a very smart guy here. I've known him for some time. He said, any small change, a perturbation, you don't know how to deal with it. All that complexity that confuses you in the world of mathematics is so simple. But by the time it reaches you to your human world, it becomes infinitely complicated. Okay? You don't know how to deal with it. Okay? But if you learn it the other way, theoretically, you could solve these problems like they're nothing. Okay? You'll classify them mathematically, and then you'll deal with them mathematically. Okay. Who was the first person who spoke?
Me, Darren.
Say your name again?
Darren.
Eric, right?
Darren. Me.
Garrett. Garrett, you got 10 points too.
Thank you.
Yeah.
Darren. Darren.
Okay, let's start with the next
Almost
video.
everything we've learned so far about probability and combinations, conditional probability. So let's say I have a bag again. In that bag, I have 5 fair points. 5 fair. And I have 10 unfair points. 10. And a fair coin, of course, is a 50% chance of getting heads or tails. And the unfair coin, let's say that there is a 80% chance of getting a heads for any one of those points, and that there is a 20% chance of getting tails, right? So either be heads or tails. So my question is what happens is I put my hand in the bag, my eyes are closed, and I picked out a coin, and then I flip it 6 times. And it turns out that I got 5 out of, well, let's say, yeah, well, no, let's say I got 4 out of 6 heads. That's the result I got. What I want to know is, what is the probability that I picked out a fair coin, given that I got 4 out of 6 heads? But before moving on, let's do a little bit of a review of Base Theorem, and I think that'll give us a good framework for the rest of this problem. So Base Theorem, let me do this corner here. Base Theorem tells us the probability of both A and B happening, that upside down view is just intersection in set theory, but it's essentially saying, you know, it's a set of events in which both A and B occur. That's equal to the probability of A occurring given B times the probability of B, which is also equal to the probability of B occurring given A times the probability. Okay. And I think this should make some intuition to you for you. If it doesn't, it might be a good idea to watch the conditional probability videos. But what we can do is we can rearrange this equation right here to get, if we just divide both sides by the probability of B, we get the probability, and I'll do this in a vibrant color, the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. I just took this equation, divided both sides by the probability of B, and I got this. So what is A and B, the problem we're trying to figure out? We want to try to figure out the probability that I picked out a fair coin, given that I got 4 out of 6 heads. So in this situation, A is that I got a fair coin. A is equal to picked fair coin, picked fair. And then B is equal to 4 out of 6 heads. 4 out of 6 heads. So in order to figure out the probability that I picked a fair coin, given that I got 4 out of 6 heads, I have to know the probability of getting 4 out of 6 heads given that I picked the fair coin times the probability of picking out a fair coin divided by the probability of getting 4 out of 6 heads in general. So this is probably the hardest part to figure out. And we will, along the way, we'll actually probably figure out the top 2 terms. So what's the probability of B, or the probability of getting 4 out of 6 heads? Let's see what happens. Right when I put my hand in the bag and I pick out a coin, there is a 5 in 10 chance, or 5 in 15 chance, right? There are 15 total coins, but I pick a fair coin. So 5 in 15, that's the same thing as 1/3. But I pick a fair coin. And then there's a 2/3 chance that I pick a unfair coin, right? Now, if I pick a fair coin, given that I have a fair coin, what is the probability? What is the probability given the fair coin? What is the probability that I get 4 out of 6 heads? Well, once again, let's think about the previous several videos. What's the probability of getting any one particular combination of 4 out of 6 heads? So, for example, it could be heads, tails, heads, tails, heads, heads. It could be, I don't know, it could be the first 4 heads, 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 tails, tails, right? And there are a bunch of these, and we, once again, we'll use the binomial coefficient, or we'll use our knowledge of combinations to figure out how many different combinations there are. What's the probability of each of these combinations? Well, what's the probability of heads? That's 0.5 times 0.5 times 0.5 times 0.5. And then the probability of tails is also 0.5 times 0.5 times 0.5. So each of these, there's a 1/2 chance of getting heads, times 1/2 chance of the tails, times 1/2 chance of the heads, times 1/2 chance of the tails, et cetera, et cetera. So each of these are essentially, 1/2 times 1/2, 6 times. So the probability of each of the combinations is 1/2 to the 6th power. 1/2 to the 6th power. And so how many combinations are there like this, where you get, out of the 6 flips, you're essentially choosing 4 heads. You're choosing, if I am once again the god of probability, I am picking probability B. We get the probability, and I'll do this in a vibrant color, the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. This equation is divided by the probability of B. So what is A and B in the problem we're trying to figure out? We want to try to figure out the probability that I picked out a fair coin, given that I got 4 out of 6 heads. So in this situation, A is that I got a fair coin. A is equal to picked fair coin, picked fair. And then B is equal to 4 out of 6. 4 out of 6 heads. So in order to figure out the probability that I picked a fair coin, given that I got 4 out of 6 heads, I have to know the probability of getting 4 out of 6 heads given that I picked the fair coin times the probability of picking out a fair coin divided by the probability of getting 4 out of 6 heads in general. So this is probably the hardest part to figure out. And we will, along the way, we'll actually probably figure out the top 2 terms. So what's the probability of B, or the probability of getting 4 out of 6 heads? Let's see what happens. Right when I put my hand in the bag and I pick out a coin, there is a 5 in 10 chance, or 5 in 15 chance, right? There are 15 total coins, but I pick a fair coin. So 5 in 15, that's the same thing as 1/3. But I pick a fair coin. And then there's a 2/3 chance that I pick a unfair coin, right? Now, if I pick a fair coin, given that I have a fair coin, what is the probability? What is the probability given the fair coin? What is the probability that I get 4 out of 6 heads? Well, once again, let's think about the previous several videos. What's the probability of getting any one particular combination, 4 out of 6 heads. So for example, it could be heads, tails, heads, tails, heads, heads. It could be, I don't know, it could be the first 4 heads, 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 tails, tails, right? And there are a bunch of these, and we, once again, we'll use the binomial coefficient, we'll use our knowledge of combinations to figure out how many different combinations there are. What's the probability of each of these combinations? Well, what's the probability of heads? That's 0.5 times 0.5 times 0.5 times 0.5. And then the probability of tails is also 0.5 times 0.5 times 0.5. So each of these, there's a 1/2 chance of getting heads, times 1/2 chance of the tails, times 1/2 chance of the heads, times 1/2 chance of the tails, et cetera, et cetera. So each of these are essentially, 1/2 times 1/2, 6 times. So the probability of each of the combinations is 1/2 to the 6th power. 1/2 to the 6th power. And so how many combinations are there like this, where you get, out of the 6 flips, you're essentially choosing 4 heads. You're choosing, if I am once again the god of probability, I am picking exactly four of the 6 heads. I'm picking 4 of exactly 6 of the flips to end up heads, right? I'm choosing which of the flips get, selected, so to speak. So it's essentially, there are going to be, out of 6 flips, I'm choosing as the god of probability 4 to be heads. So that's the number of combinations, the number of unique combinations where you have 4 out of 6 heads, times the probability of each of the combinations, which is 1/2 to the 6th power. Well, what's 6 choose 4? That's 6 factorial over 4 factorial times 6 minus 4 factorial, so it's 2 factorial. And that's times 1/2 to the 6th. Switch colors again, just stop the rounding. That equals 6 times 5, 4 times 3 times 2. We don't have to write the 1 times 1, I'll do it anyway. Over 4 factorial, 4 times 3 times 2 times 1, and then 2 factorial, 2 times 1. So that cancels with that. The 1 we can ignore. 2 divided both sides by the numerator and denominator by 2, 3. So this becomes 15. So this equals 15 times 1/2 to the 6. What's 1/2 to the 6? That's 1 over 64, right? So 1 over 64, so it becomes 15 over 64. So the probability of getting 4 out of 6 heads given a fair coin is 15 out of 64. So this is the probability of 4 out of 6 heads given a fair coin. And if you look at it, based on our definition of B and A, this is the probability of B given A, right? B is 4 out of 6 heads given a fair coin. Fair enough. So let's figure out the probability of, because there's 2 ways of getting 4 out of 6 heads. One that we picked a fair coin, and then, times 15 out of 64. And then there's a probability that we picked an unfair coin. So what's the probability of the unfair coin? Of getting 4 out of 6 heads given the unfair coin? But once again, what's the probability of each of the combinations we get 4 out of 6? So in this situation, let's do the same one. Heads, tails, heads, tails, heads, heads. Right, that's 4 out of 6 heads. But in this situation, it's not a 50% chance of being heads, 80%. So it would be 0.8 times 0.2 times 0.8 times 0.2 times 0.8 times 0.8. As essentially we have, this multiplication, we can rearrange it because it doesn't matter what order you multiply things in. So it's 0.8 to the 4th power times 0.2 squared, right? And it doesn't matter, any of the unique combinations will each have the same probability because we can just rearrange the order in which we multiply, right? And then how many of these combinations are there? If we are, once again, the god of probability, and out of 6 flips, we are picking 4, we're choosing 4 that are going to end up heads. How many ways can I pick a group of 4? Well, once again, that's times 6 choose 4. And we figured out what that is. 6 choose 4 is 15. So this equals 15 times 0.8 to the 4th times 0.2 squared. So the probability, So this is the probability of 4 out of 6 heads given an unfair coin. So what's the total probability of getting 4 out of 6 heads? Well, it's going to be the probability of getting the fair coin, which is 1/3, times the probability of getting 4 out of 6 heads given the fair coin, and that's this, 15 over 64, times 15 over 64, plus the probability of getting an unfair coin, 2/3, times the probability of getting 4 out of 6 heads given the unfair. That's what we figured out here. Times 15 times 0.8 to the 4th times 0.2 squared. And this is the probability of getting 4 out of 6 heads. Let's figure out what that is. Well, this will cancel out. This is 5 out of 4. That's easy enough. 2/3 times 15. That's 10. And we just figure out what that is. Let's see. I'm going to go over the time limit to see if being a U2 partner allows me to go over the time limits. 0.8 times 0.8 times 0.8 times 0.8 is equal to, and then times 0.2 squared, so times 0.2 times 0.2 is equal to 0.016. So that's that. Then we say times 10, right? Because 2/3 times 2 times 10 is equal to 16.384%. So the probability is, so this term right here, so let's switch colors. This is 0.16384. We're going to add that to 5 divided by 64. 5 divided by 64 is equal to 0.07, whatever, plus 0.16384 is equal to 0.241965. So that's the probability, not knowing which coin I picked out. That's the probability of getting 4 out of 6 heads. When you combine it, it could be 1/3 chance fair, 2/3 chance unfair. So that's 24.19. I'm keeping the precision just because it might come useful later. % chance. So that's the probability of B. So let's see if we can clean this up a little bit, just because I don't think we need all of this writing now. I think we're ready to substitute it to our Bayes formula, Bayes theorem that we re-derived. Writing longer videos is dangerous because if I make a mistake, that's more time wasted. Okay. So let's see if we can solve the probability that we picked a fair coin given that we got 4 out of 6 heads. So that is going to be equal to, by Bayes theorem, which should make some sense to you, that is equal to the probability of B given A. So it's the probability that we get 4 out of 6 heads given a fair coin times the probability of a fair coin over the probability of getting 4 out of 6 heads either way. 4 out of 6 heads. So 4 out of 6 heads given a fair coin, we figured that out over here. That's 15 over 64. So this equals 15 over 64. What's the probability that we picked a fair coin? Well, there's 15 coins and 5 of them are fair, so it's 5 out of 15, so it's 1/3. 1/3. And what's the probability that in general we picked 4 out of 6 heads? Well, that's this number, 0.241965. This equals, let's see, this is equal to 5 over 64 divided by 0.241965. What is that? 5 divided by 64. Equal to that. Divided by 0.241965 is equal to roughly 3%, is equal to 32.3%. So that's amazing, or relatively amazing. It's a little bit less than a 1/3 shot that we picked the fair coin, given that we got 4 out of 6 heads. And what's interesting is the 4 out of 6 heads kind of decreased the probability that we got a fair coin, right? Because before having any data on what happens with flipping, we would have a 1/3 probability, which is 33.3, right? But given that we got more heads than tails, kind of the universe of probability is telling us that, well, if you got more heads than tails, that makes it a little bit more likely that you pick the unfair coin, which is a little bit more weighted to heads. We're saying it's not that much more likely because this isn't that unusual of a result to get even with a fair coin. And so that's why it became a little bit less likely to get a fair coin. I will actually, and let me give you a bit of an intuition visually, kind of set theory on why that makes sense. Why that makes sense. If we go back to Base Theorem, let's just say that, this is the universe of all of the events, right? That's all of the universe. There's roughly a 1/3 chance that I picked a fair coin. So roughly 1/3 of this will be fair. This is fair. This is unfair, right? And then if I picked a fair coin, we figured out there's roughly a 15 out of 64 shot that I get 4 out of 6 heads. So maybe that's this little section of it. Let me do a different color. That's this section. And then we figured out if we have an unfair coin, I forgot what the exact number is, but there was some probability that we get 4 out of 6 heads, right? It's actually a little bit bigger. It's like that, right? So this is getting 4 out of 6 heads given you got an unfair coin. This is getting 4 out of 6 heads given that you got a fair coin. And then this whole area is a probability to get 4 out of 6 heads. So all Bayes' theorem told us is, look, we got 4 out of 6 heads. So we're in this universe where we got 4 out of 6 heads. And if we got 4 out of 6 heads, 1/3 of this universe, roughly, or 32.3% of this subset of 4 out of 6 heads, intersects with the fair coin universe, right? So this 32.3% is essentially this fraction of the total probability of getting 4 out of 6 heads. Anyway, hopefully that gave you a little bit of intuition, and I hope that YouTube lets me publish this video because I'm on my 17th minute. I'll see you in the next video.
In this lesson, we're going to focus on something called conditional probability. Perhaps you've seen something like this. P of A, a bar next to it, and then a B. What does this mean? This represents the probability that event A will occur given that event B has already occurred. So let's say we have a 6-sided die with a sample space of the numbers 1 all the way to 6. And let's say that event A is any time we get an even number by rolling, well, let's say an odd number when we roll it out. So 1, 3, and 5. And event B, let's say that corresponds to the numbers 3, 4, and 5. So what is the probability that event A will occur given that B has already occurred? Before we get into the formula, let's talk about a quick and simple way of getting the answer. Ask yourself this question: how much of A is in B? The elements of A that is in B is 3 and 5. So there's 2 elements of A that is in the 3 elements of B. So 2/3 of B is basically from A. So that's the probability of event A occurring given that event B has already occurred is 2/3. That's a quick and simple way to do conditional probability. But now there's a formula that you need to know. To calculate this conditional probability is the probability of event A and event B occurring divided by the probability that event B will occur. So what is the probability of getting event B? B has 3 outcomes that lead to it. out of a total of 6 outcomes in the sample space. So when you roll a 6-sided die, there's 6 numbers you can get, and B is half of those numbers. So the probability that event B will occur is 3 out of 6. Now, what about the probability of events A and B occurring? Well, let's write the sample space for A and B. So this is the intersection of A and B. And we know that the numbers 3 and 5 corresponds to A and B. So event A and B will occur if we get 2 numbers out of the 6 potential numbers that we could get. So the probability of A and B occurring is 2 over 6. Now, to simplify this complex fraction, let's multiply the top and bottom by 6. So that the number 6 will cancel. And so we're left with 2 over 3, which is the same as what we see here. So that's a simple way in which you can calculate the conditional probability of an event occurring. But now let's look at some more example problems. There are 500 students in a certain school. 150 students are enrolled in an algebra course, and 80 students are enrolled in a chemistry course. There are 30 students who are taking both algebra and chemistry. If a student is chosen at random, what is the probability that the student is taking algebra? Before we begin, let's draw a Venn diagram. So we're going to draw 2 circles with the circles intersecting each other. Let's put A for algebra and C for chemistry. So there's 150 students taking algebra, and there's 80 students taking chemistry. There's 30 taking both. And in this school, there's a total of 500 students. So what is the probability that the student is taking algebra? So there's 150 students taking algebra out of a total of 500 students. So this becomes 15 over 50. 15 is 5 times 3, 50 is 5 times 10. And so the probability of selecting an algebra student is 3 over 10, which is 0.3 or 30%. Now, what about part B? What is the probability that the student is taking chemistry, given that the student is also taking algebra? So this is a conditional probability problem. So we're going to find the probability of getting C, given that the student is taking algebra, or given A. So how much of C is in A? Think of it that way. We have 30 of C that is in A. So it's going to be 30 out of 150. Now, for those of you who prefer to use the formula, this is going to be the probability of getting C and A divided by the probability of getting A. So the probability of getting C and A, the probability that a student is taking algebra and chemistry is 30 out of a total of 500 students. The probability of a student taking algebra, that is the probability of A, is 150 out of 500, which we calculated earlier. And so multiplying the top and the bottom by 500, you can see we're going to get the same answer. It's going to be 30 over 150. So let's simplify 30 over 150. 30 is 30 times 1. 150 is 30 times 5. So the probability is going to be 1 over 5, which is 1 divided by 5 is 0.2. So there's a 20% chance of selecting a student who is taking chemistry, given that they're taking algebra. Now, let's talk about what this means. Out of all of the 150 algebra students in the school, 20% of them is taking chemistry. 20% of 150 is 30. Now, let's move on to the last part of this problem, part C. What is the probability that the student is taking algebra, given that the student is also taking chemistry? So going back to part B, we said the probability of getting C given A was 1 over 5. Now, in this problem, we're looking for something different. We're looking for the probability of A given C, and these are not the same. So what is the probability of selecting a student who is taking algebra, given that that student is taking chemistry as well? So how much of A is in C? Notice that we have 30 of A that is in basically 80 of C. So this is going to be 30 over 80, which we can reduce that to 3 over 8. So out of the 80 students who are taking chemistry, 30 of them is taking algebra. So the probability of selecting a student that is taking algebra, given that they're taking chemistry, is 3 out of 8. And so that's a simple way in which you can do conditional probability calculations. Let's move on to the next question. There are 200 birds in a zoo. 70 birds are male with brown eyes, and 100 birds are female with brown eyes. 20 of the birds are male with blue eyes, and 10 birds are female with blue eyes. Construct a contingency table. So let's begin by doing that first. So on the left, we're going to have the gender. So it's either male or female. And at the top, we're going to put the color of the eyes, either blue eyes or brown eyes. Pick a different color for this. And at the sides, we're going to put the totals. So 70 birds are male with brown eyes. So let's put a 70 here. 100 birds are female with brown eyes. 20 birds are male with blue eyes. 10 birds are female with blue eyes. So what's the total number of males? 70 plus 20 is 90. Now the total number of female birds is going to be 100 plus 10, which is 110. So adding these two will give us a total of 200 birds in this zoo. Now let's add these numbers. So the total number of birds with brown eyes is 170. The total number of birds with blue eyes is going to be 30. And we can see that 170 plus 30 is 200. So now that we've filled out the contingency table, let's answer some questions. If a bird is selected at random, what is the probability that the bird is a female? So let's start with that. So what's the probability of getting F? So there's 110 birds that are female out of a total of 200 birds in the zoo. So the probability is going to be 110 over 200. If we divide both numbers by 10 by getting rid of the 0, the probability is 11 over 20, which is 0.55, or a 55% chance of selecting a female bird. Now, what about selecting a bird that is a male with brown eyes? So this is not a conditional probability question. We're looking for a bird with two characteristics. It has to be a male and it has to have brown eyes. So there's 70 birds that are both male and with brown eyes out of a total of 200 birds. So the probability is going to be 7 out of 20, which is 0.35, which corresponds to a 35% chance of selecting such a bird. Now let's move on to part C. So what is the probability that the bird is a female given that it has brown eyes? So now we're dealing with a conditional probability question. So what is the probability that we're going to get F given BR? So to do it the easy way, think about this question. How much of F is in BR? So out of all the birds with brown eyes, how much is female? So there's 170 birds with brown eyes. 100 of those birds are female. So it's going to be 100 out of 170, which reduces to 10 over 17. Now, if we divide 10 by 17, that's going to be 0.588. So let's talk about what this means. That means there's a 58.8% chance of selecting a bird that is a female, given that the bird has brown eyes. So out of all of the 170 birds with brown eyes, 58.8% of those birds are female. So that's what that means. Now let's move on to part D. What is the probability that the bird is a male, given that it has blue eyes? So what's the probability of M given BL? So how much of M is in BL? There's 20 of M and 30 of BL. So there's a total of 30 birds with blue eyes, 20 of which are male. So the probability of selecting a male bird, given that it has blue eyes, is 2 over 3. So as you can see, it's really not that difficult when calculating conditional probability, if you understand the principles behind it. Now, before we answer the last question, I just want to clear away a few things, because this page is getting crowded now. So the last part, what is the probability that the bird is a creature with blue eyes, given that it's a female? So what's the probability of BL given F? So how much of BL is in F? So there is 110 female birds, 10 of which contain blue eyes. So the probability is going to be 1 over 11. There's, out of all the 110 female birds, 10 of those have blue eyes. And so this is it. That's all you got to do is 10 over 110, which reduces to 1 over 11. And let's turn that into a decimal value. So that's approximately 0.091 if you round it. So there's a 9.1% chance of selecting a bird with blue eyes, given that.
So that's it for tonight. Let me see. Carson, can you hear me? Carson,
Oh,
Carson, can you hear me?
yeah.
Okay. So that's it for tonight. For next week, we have chapter 5 only. The only homework we have to do is the chapter 5 homework on Connect, okay?
Okay.
And I'll see you next week.
Yeah. Thank you.
Have a good night.
Thank you.